This came in CSIR net. I think June to 2015. So an ideal Bose gas in d dimensions obeys the dispersion relation epsilon k is equal to a k to the power s. For Bose-Einstein condensation to occur, the occupancy of excited states, this thing is the occupancy of excited states, Ne, should be finite even for mu is equal to 0. That means z equals to 1, the small z. Then what is the inequality between D and S? Can anyone say? Just let me ask. It should be a bi-directional thing. How will you tackle this problem? This is a 5-mark question. So this integral should be finite even for mu equals to 0. So that means for mu equals to 0, there will be this thing, Bose-Einstein condensation. So what is the formula to tackle this problem? Can anybody give some idea? Starting? Do you know this formula? Yes or no? Just a minute.
Sir, no idea, sir.
Just a minute. Yeah. So how will you tackle this problem?
Sir, no idea, sir.
No idea. No idea. Does anyone have some idea? So what is, okay, have you done Bose-Einstein statistics? Have you done that Bose-Einstein statistics, free Bose gas in 3D, non-relativistic Bose gas in 3 dimensions?
Eighth exam, net exam மட்டும் பிசிக்ஸ்லயும் மேத்ஸ்லயும் நெட் கிளியர் பண்ணிருக்காரு. கேட் எக்ஸாம் வந்து 3 சப்ஜெக்ட்ல கிளியர் பண்ணிருக்காரு.
Yes.
ஐஐடி கவுஹாத்தில PhD பண்ணாராம்.
Who is opening the... So how do you do this? Okay, let me start. Rather than... So this integral is called, let's say, this integral. So this integral 1 by gamma nu integral 0 to infinity x to the power nu minus 1 dx by z inverse e to the power x minus 1 is called g nu z, which is the Bose-Einstein integrals. Okay. So this equals to this g nu z, you can write it to be sigma summation n is equal to 1 to infinity z to the power n by n to the power nu. Okay. These are called the Bose-Einstein integrals. So now you see, this is of the form Ne equals to C into gamma d by s g d by s z. Can you get this integral? G d by s z, where d is the dimensionality of the system and s is this E equals to a k to the power s. That means E equals to a p to the power s. So if you want this to be finite, even for mu equals to 0, so for mu equals to 0, you have z equals to 1. So g d by s 1 is the zeta d by s, where this zeta is the Riemann zeta function. So the number Ne is some constant into gamma d by s zeta d by s, where this zeta, the Riemann zeta function of d by s, is summation n equals to 1 to infinity 1 by n to the power d by s. This will only converge when d by s is greater than 1. So that will be your answer. So I think the answer is d by s greater than 1, which is 3. Option is, I think, C. So did you get this? This is just, if you know this integral, it will be done in within 30 seconds. You have to know this. Even you can do it from here, that Bose-Einstein integrals will be converging if the power nu z to the power m by n to the power nu, when nu is greater than 1. Says here is d by s. So do you have any doubts? So the dimensionality of this Bose gas must be greater than equal to the power spectrum. This is called dispersion relation of the bosons. So if you have 3, dimensionality is 3, that the Bose gas in 3 dimension and a non-relativistic dispersion relation, then 3 is greater than 2. So this g d by s is g 3 by 2 z. So you can have Bose-Einstein condensation in 3 dimensions with non-relativistic Bose gas. But if your dimension is 1 and you have a non-relativistic Bose gas, then the Bose-Einstein condensation will never occur. Please remember, Bose-Einstein condensation will only occur if D is greater than S. If you have any doubts, please stop me and ask.
ஜாயின் ஆகுது கேதோ
Okay.
இது வந்திருக்கு NWPS 2023.
Anyone asking? Or you can write it in the chat box. Next question is the specific heat. Question of the specific. This is in the 2011 CSIR net. This is, it says, the excitation of a 3D solid are bosonic in nature with frequency omega and wave number k. And they're related by omega is directly proportional to k square in the large wavelength limit. If the chemical potential is zero, then Cv is directly proportional to T to the power what power? So you see, this is 3D, so dimension is 3. And omega is directly proportional to k square. That means E is directly proportional to p square. So now, if I do, see, this is D is 3 and S is 2. So I will generalize it to D. This can be applicable to any problem. So D, dimension D is D, and this omega is directly proportional to k to the power s. Then what is the Cv? Now you see, when you did your GPdP, that is the density of states in momentum space, you have did in 3 dimension 4 pi p squared dp. So whatever it is, if you do density of states in d dimension space, GdP this is directly proportional to p to the power d minus 1 dp, which is directly proportional to k to the power d minus 1 dk, because p is h cross k. I'm just taking the order, not about this whatever constants are there. Now omega is directly proportional to k to the power s. Therefore k is directly proportional to omega to the power 1 by s. Therefore G d p dp is k to the power, so this is of the order of k to the power d minus 1 dk. This is of the order of omega to the power d minus 1 by s d of omega to the power 1 by s. So this is omega to the power d minus 1 by s into omega to the power 1 minus s by s d omega. So this is equals to omega to the power d minus s by s d omega. So therefore, your internal energy U is equals to, so it is directly proportional to some VD by some h to the power 3 by d, whatever. I am not writing that. So it is directly proportional to integral 0 to infinity EP FP GP into dP, where FP is the Bose-Einstein distribution function. So these, because of these solids, the excitations are bosonic in nature. So this is directly proportional to integral 0 to infinity. This omega, so EP is h cross omega into G, this is GP dP. You can, this is also, you can write it in G omega, such as this GD omega d omega. So omega into omega to the power d minus s by s d omega. Now the chemical potential is 0. So e to the power beta h cross omega minus 1. So this is directly proportional to omega to the power d by s d omega e to the power beta h cross omega minus 1. Now, if you change the variables from beta h cross omega as x, you can write this is directly proportional to 1 by beta to the power d by s plus 1 integral beta h cross omega whole to the power d by s t of beta h cross omega by e to the power beta h cross omega minus 1. So this, for this is what? This is zeta of d by s plus 1. Some number, but you have already got beta to the power d by s plus 1. So u is directly proportional to t to the power d by s plus 1. Therefore, CV is always directly proportional to t to the power d by s. Did you get it? So that means here d is 3, s is 2. So CV is, in this case, omega directly proportional to k square. With a 3D solid, CV is directly proportional to t to the power 3 by 2. If d is 3, s is 1, that is relativistic case. If it is relativistic, then CV is directly proportional to TQ. So in general, zero chemical potential systems in d dimensions and with s omega directly proportional to k to the power s will be CV directly proportional to t to the power d by s. Did you get it? If you have any doubts, you can ask. This is just order of magnitude calculations. You do not need to know what is the constants before. H cross C and all this V. You need to know, they will only ask you the temperature dependence of CV, which is the most important thing. We use the temperature dependence of specific heat.
So dispersion relation will be given.
Dispersion relation will obviously be given. Obviously, if they ask photons, they will assume that you know the dispersion relation. Or phonons, they will assume that you know the dispersion relation. If these types of particles are known as this magnons, okay, these are excitations in ferromagnets. So omega directly proportional to k square. So anyways, whatever it is, you do not need to know. You need to know what is E directly proportional to P to the power S and what is the dimensionality D. And always note that P, if you use this, you will know P is equal to what? S by D into U by V, always. P is equal to S by D into U by V. In this non-relativistic, you did 2 by 3 into U by V, and in extremely relativistic, it was 1 by 3 into U by V. So it is in general S by D into U by V. So you see, this is the U, that is the energy, internal energy is omega to the power D by S d omega by E to the power beta H cross omega minus 1. The last problem which I did was this number of particles. Obviously, number of particles will be 1 omega smaller because I have number of particles. So number of particles is just integral some constant 0 to infinity, just integral ft gp dp. So this is some integral 0 to infinity. So if you have gp dp is omega to the power d by s minus 1 d omega by e to the power z inverse e to the power beta h cross omega minus 1 if there is non-zero chemical potential. So that is exactly equal to that formula which is given in this question. Please remember this. This question, if you know Bose-Einstein integrals and Riemann zeta function, this will be done in just 30 seconds. And this also, basically this you don't have to do much. If you even memorize, that will be good. Okay. So any doubts? Now let us do one more problem. That is this average quantity of something. This came in the GATE 2013. So in this GATE 2013, they gave question is find this average. I'm not writing the full question. E to the power I, A vector dot P vector whole average for a gas of particles with mass m at temperature T obeying MB statistics. Classical. Obeying MB statistics. So this came in 2013. So how will you proceed? Obviously, how will you find this e to the power I a vector something, some average? Let's say a average of A. How do you do it? Something average quantity of something. in thermodynamics, statistical mechanics? How do you do? What? Tell me, someone tell me. How do you do it? Just give me the starting point. How do you calculate the average of something, thermodynamic average or ensemble average, what you call? How do you do it? Let me see. You can raise your hand. What happened? Just give me the starting point. You don't have to do the whole thing. Just tell me the starting from which you can calculate, and that calculation you can do later. How do you do it? What is it difficult? How do you calculate average? Thermodynamic average. What happened? You are not interacting. Am I audible or not? Now I'm doubting myself. Hello.
Sir, you are audible, sir.
Yeah, but I think so. How do you start from? We have done this. Some E average, internal energy average. This how do you start? Say something average. Some quantity average. How do you start? So let's say in canonical ensemble using canonical partition function. How do you do it? Let's say this.
Participants, please be interactive. Then only it's going to be beneficial to all.
How do you do it? So do you do like this? By Z? Is it familiar to you? How do you calculate the energy, average energy? So let's say average energy, how do you calculate? By Z, where Z now is it looking familiar to all of you?
Yes, sir.
Yes. So any quantity which you calculate average, you have to sum with that quantity into e to the power minus beta ei divided by the partition function z.
Dr. Somnath, can I interrupt you?
Yes, sir. Yeah.
Yeah. I just need a small clarification.
Yes, sir.
When you do this ensemble average, you use this expression exponential I ai e power minus beta ei
Beta ei,
by,
yes,
by
yes.
z.
Yes.
Z is the
Yes.
partition function.
Partition function. Yeah.
Yeah. So the moment you use this factor, the Boltzmann factor e power minus beta ei,
Yes, yes.
is it correct to say that the underlying statistics is Maxwell-Boltzmann?
Yeah, because in that question they have said MB statistics.
Yeah, I
So-
understand that.
Ah.
Yeah, I understand the question. My doubt is, if you
No,
use
no,
this
no.
kind of averaging,
If this is not Maxwell-Boltzmann, then you cannot do like this.
okay,
So
okay,
this is
okay.
just a case of, actually this is first, you can take an ensemble average using this canonical ensemble.
Correct.
If it is grand canonical, then you have to do beta ei minus mu ni.
Correct. Okay.
So this is canonical ensemble, MB statistics.
Yeah. Okay. Okay. Please.
So, okay. So did you understand this? So now in a gas of particles, we use this gas because there are so many particles with so many closely spaced energy levels that it is not possible to do it using summation. So we do it using integration. How do we do the integration now? Again, what is the partition function? So partition function is using this thing. Now, this partition function of a Maxwell-Boltzmann gas statistics, I told you it is V by lambda. But here you can also do it like this. So what I did was I have used this partition function by writing this is 1 by h cube integral 0 to infinity e to the power minus beta p square by 2m d3p into integral 0 to L, if you want to say. So this is d3 dx dy dz. So basically it's v. So this is something in d3x, right? Now d3x, there is nothing. The energy doesn't contain the function x. So this is v. So you just put v. So v by h cube integral 0 to infinity in e to the power minus beta p square by 2m d3p. And last I said d3p is 4 by p square dp. If you take in the spherical polar coordinates, in this p space, you take for spherical polar coordinates. But here, see this, you are doing this quantity average. E to the power I a vector dot p vector. So this e to the power I a is some vector, constant vector, independent of p or x. So this is e to the power I ax px plus ay py plus az pz. Now you see this has come as px, py, pz. So if you do in 4 pi p squared dp, it will be difficult. Why it will be difficult? I'll tell you. Instead, you can also do d3p in the Cartesian coordinates in momentum space as dpx, dpy, dpz. Okay, so this you can do like this: integral minus infinity to infinity e to the power minus beta. See, p square by 2m. P square is px square plus py square plus pz square. So e to the power minus beta px square by 2m plus into e to the power minus beta py square by 2m into e to the power minus beta pz square by 2m into dpx, dpy, dpz. This dpx, dpy, dpz will all range from minus infinity to plus infinity. So this is e to the power minus beta px squared by 2m dpx, integral minus infinity to infinity e to the power minus beta py squared by 2m dpy into integral minus into e to the power minus beta pz squared by 2m dpz. Now, don't calculate this integral now, because why I am doing it is I will tell you after some time. These types of problems where you have exponential of something with a single power of p, you will see what will happen. They will cancel later. What is the numerator? So you have e to the power I a vector dot p vector average is v by h cube into integral minus infinity to infinity e to the power I x px into e to the power minus beta px square by 2m dpx integral minus infinity to infinity e to the power I ay py e to the power minus beta py square by 2m dpy into integral minus infinity to infinity e to the power I az pz e to the power minus beta pz square by 2m dpz by z. Did you get this, everyone? This expression, are you following?
Dr.
Yes, sir.
Somnath,
Participants, are you following? Are you following this expression? How did I get it?
Yes, sir.
Yes, sir.
Okay,
Dr.
good.
Somnath, can I interrupt you?
Yes, yes, sir.
Yeah. So you are taking the average of e power IAP.
I affected dot yeah.
Yeah. Now this e power minus beta p square. That is
Because
supposed to,
this
oh, that is the
numerator
factor
is
of
basically
hmm.
v by h cube integral. If you do in spherical polar, so basically this is e to the power I a vector dot p vector is e to the power I ax px into e to the power I ay py into
So that
e
I
to the power I
understand.
az pz. Yeah.
Yeah.
So
So
now
how
you
do
have
you
to
get that e power?
integrate with this factor e to the power minus beta p square by 2m t3p. You have to integrate with this factor and divide it by the partition function z.
No, when you take this e power beta p square by 2m,
Yes, sir.
that is actually a free particle energy, right?
Yeah. When we say it is nothing, it is a free particle. Free particle. All are
Oh.
free. Yeah.
Okay. So you, in addition to free particle, you have this potential kind of, isn't it?
Sir, this is not potential. This is some, you can say it is some sort of a quantity a dot p, where I have to include this a dot p into e to the power minus beta px square by 12.
Okay,
This,
okay, fine.
this quantity may be anything. This quantity may be even some function of p also,
Okay.
or some function of x. If
Oh,
it
you
is
have,
x, then I have to include dx also in the integral. I cannot take out v, dx, dy, dz.
okay, you are saying that average is taken with the e power minus beta p square term.
Yes, yes, sir. Yes,
Oh,
yes.
Okay, please proceed.
So
Thank
this
you.
is the expression. Remember, if this was a function of x, this was a function of x, then I cannot take this v out because this is a double integral. Integral fxp dpx dx. So you cannot take this integral out. So if you have to first integrate with respect to p, then it will be some function of x, some gx. Then you have to integrate with gx with respect to dx. Then it will be independent of x. So, but that is a very, they will not give you so hard integrals. That's why I'm saying that in that expression of this partition function here, I am telling you not to evaluate this integral. This integral is basically root 2 pi m by beta. This is a very, but don't evaluate this integral if you do not know. It will be a waste of time. So now the main thing is how you have learned, how can you do this integral? Because if you do one integral, you can do the other integrals also. How can you do this integral? Let's say integral minus infinity to infinity e to the power ix px into e to the power minus beta px square by 2m dpx. Can anybody tell me how to do? If you know how to do this, you are done with this problem. You did this integral previously. Can anybody tell me how do you do this integral? Ashwin?
Sir, actually, it's tough
Huh?
to follow, sir. No idea. I'm just listening.
This integral, just I give a hint, complete the squares. So this is minus infinity to infinity, e to the power, I'm writing. You have to complete this as a whole square. E to the power minus something square to dpx. Do you know how to do this? Complete the squares. This is a quadratic function. This is a linear function of p. Then the other function will be independent of p. So just check this. Just check this. So this is integral minus infinity to infinity e to the power minus beta by 2m px minus I m a x by beta whole square dpx into a constant term e to the power minus ax square m square by beta square into beta by 2m. So this I have made it as a whole square. E to the power minus some constant into px minus some another constant square dpx. Are you following, all of you? This integral, I have made it as a whole square into some constant which is independent of px. So this I can take out of the integration. Are you following? Yes or no?
Yes, sir.
If you don't respond, then I cannot able to know whether you are following or not. All of you. What happened? Kiran, are you following?
Sir, it seems quite difficult.
Seems quite difficult. No, what is difficult is you have to create this square.
When you have to assume that taking a square term, so that was difficult. After that,
This is the most difficult thing here.
yeah.
How to make this as a whole square? This is completing the squares in integration. Now, this question came out in the problem of an integration. Now see, if you do this for x, another term will come for y, another term will come for z. So the e to the power I a vector dot p vector average will be v by h cube into z. I'm writing zh cube integral minus infinity. Okay, I will first write these terms. So this beta and m and n will be cancelling. So e to the power minus ax square plus ay square plus az square into m by 2 beta into integral minus infinity to infinity e to the power minus beta by 2m into px minus imax by beta whole square dpx into integral minus infinity to infinity e to the power minus beta by 2m into py minus imay by beta whole square dpy into integral minus infinity to infinity e to the power minus beta by 2m into pz minus imaz by beta whole square dpz. Now, you see, this what, okay. If you change the variable px prime, this quantity does not depend on px. So I can easily change the variable from px to px minus imax by beta. Do you get it? So I can do this. Px prime is equal to px minus imax by beta. Therefore, the first x integral comes, the limits will be the same, e to the power minus beta by 2m, px prime square dpx prime. Just change this variable, px prime to px minus imax by beta. Then this integral will come the same as integral in the partition function z. That is why I did not want to evaluate this partition function. So you see, this quantity will cancel with the denominator, whole quantity. This part will cancel. So your leftover is e to the power minus m square by 2 beta, which is equals to e to the power minus half m square kbt. So your option is, I don't know what is the option, but I think it is C or B, whatever. Participants, did you get what I have done here?
Sir, how they cancel each other?
How they cancel? So what is this integral? E to the power, let me take this integral. Integral minus infinity to infinity. E to the power minus beta by 2m px minus imax by beta whole square dpx. So what will you do? Put some px prime equals to px minus imax by beta. Therefore, dpx prime equals to dpx. So here, this integral will be minus infinity to infinity e to the power minus beta by 2m px prime square dpx prime. In the denominator, you have another integral minus infinity to infinity to the power minus beta px square by 2m dpx from the partition function z. So aren't these two integrals the same? Huh? Can you get it? Who was asking?
Sir, yes, sir.
Can you get it?
Yes, sir.
So what does that mean? So these two integrals will cancel out. So the leftover is this e to the power that term. The answer is that, I think, this one into, so this one into z by z is your this average. So this question is given just to check your knowledge of integration. And this was given in GATE 2013. Okay. I did this in another slide. I just love it. So everyone is clear? This question?
Yes, sir.
Okay. So we'll move on to another question. This is easier. This is GATE 2019. So this is consider a 1D gas of NaCl. n non-interacting particles of mass m with the Hamiltonian of single particle given like this: H equals to p square by 2m plus half m omega square into x square plus 2x. The high temperature specific heat in units of R equals to n kb is how much? So there is a theorem which you need to use. Can anybody say what is this theorem using this Hamiltonian? The Hamiltonian is given.
Equipartition of energy. Sir.
Equipartition. Very good. Very good. Equipartition theorem. So here, high temperature specific heat means it's a classical system, and classical system we can apply equipartition theorem. So what is equipartition theorem? That if you take the Hamiltonian, how many number of quadratic degrees of freedom are there in the expression? Each quadratic degree of freedom will give you half kBt. So the Cv for one particle, this is for one particle, is for p square by 2m you will get half kBt, because this is 1d. Remember, if it was 3d it was be 3 by 2 kBt. So it is 1d, so it is half kBt, and for x square, half m omega square x square, you will get another half kBt. This will not get anything. This is not a quadratic degree. So this is kBt. Therefore, Cv for n particles is n, sorry, not Cv. This is, I'm so sorry. This is average energy. So average energy for n particles is n kBt. Therefore, Cv is n kB. So the high temperature specific heat in units of n kB is 1, which is answer is A option. So this is exactly application of equipartition theorem, where you have degrees of freedom, quadratic degrees of freedom will give you, if it is in d dimension, so it will be giving you d by 2 kBt, one quadratic degree of freedom. So it is half kBt plus half kBt, here it is kBt, your average energy. Okay. Then, yes.
Yeah, you have a term x which will cancel off when you integrate from
No, actually, this term x will not give thermal energy. This term x will be the, if you can say, it is like a sort of a some residual energy which will not give any temperature dependence. So if you don't have temperature dependence, your derivative of that energy, del U del T, that will not matter. If you do this at the partition function and calculate the average energy of this, you can do it. I mean, any one of you can try.
Sir, or if we can rearrange the terms, we can say it's like shifted harmonic oscillator. So energy
You can
average
do
is,
it. Yes, yes, you can. You can.
yeah.
Anyways, whatever you want to know is the squared term, the quadratic term. How many quadratic terms are there? The number of quadratic terms will be the number of d by 2 kBt adding to the specific average energy, and d by 2 kb in the specific heat for one particle. This another question I had. Now, another question. This is CSIR net question. Don't know. An ensemble of non-interacting spin half particles is in contact with a heat bath at temperature T. It is subjected to an external magnetic field each particle can be in one of the two quantum states. Quantum states of energies they have given. Energies plus minus epsilon 0. If the mean energy per particle is minus epsilon 0 by 2, then what is the free energy per particle? Okay. What is the free energy? How will you tackle this? This is a simplest problem. Tell me. So where shall I start from? So you are considering only one particle. See what is the free energy per particle, and each particle can be in one of the two quantum states of energies plus minus epsilon 0. So what is the partition function of one particle? Can anybody tell me?
Minus
Yeah.
beta epsilon naught, e raised to power minus beta epsilon naught plus e raised to power plus beta epsilon naught.
Correct. Z is equal to Z1. I'm writing Z1 means partition function for a single particle. single particle, e to the power minus beta epsilon 0 plus e to the power beta epsilon 0. This is 2 cos hyperbolic beta epsilon 0. So now they have given that the mean energy per particle is minus epsilon 0 by 2. So what is the mean energy? Mean energy, can you calculate? How did we do the mean energy? Just now calculate the average energy per particle of one particle.
Sum of all the energy states into e to the power minus beta I divided by the partition function.
So what will be this? Epsilon 0 e to the power minus beta epsilon 0 minus epsilon 0. This is because it is minus epsilon 0 e to the power beta epsilon 0 by z. So this is epsilon 0 into e to the power minus beta epsilon 0 minus e to the power plus beta epsilon 0 by e to the power minus beta epsilon 0 plus e to the power beta epsilon 0. So this is minus epsilon 0 tan hyperbolic beta epsilon 0. Okay. Now this is already given as minus epsilon 0 by 2. They've given. So that means this thing tan hyperbolic beta epsilon 0 is half. Tan hyperbolic beta epsilon 0 is half. Then this, what is the free energy? Then free energy F is what? Per particle. Free energy F per particle is what? How much it is in terms of Z?
Minus KBT ln Z.
Okay. So why only one person is saying and not the others? Minus KBT F1 is minus KBT ln Z1. Okay. So this is what? Minus KBT ln of 2 cos hyperbolic beta epsilon. So now we have to make this tan hyperbolic beta epsilon 0 to cos hyperbolic beta epsilon 0. How will you do it? So sine hyperbolic beta epsilon 0 by cos hyperbolic beta epsilon 0 equals to half, which implies this is root over of cos hyperbolic square beta epsilon 0 minus 1 by cos hyperbolic beta epsilon 0 equals to half, which implies, so if you do it, if you square it, I'm not doing the full thing, you will get cos hyperbolic beta epsilon 0 equals to 2 by root 3. I think, yeah. 2 by root 3. Cos hyperbolic beta epsilon 0 is 2 by root 3. If you solve this, Just square both sides and solve. Now, tan hyperbolic beta epsilon 0 equals to half. Now you have to, the answer is not given in terms of ln some constant kbt. So if the answer would have been given in minus kbt, then it would have been just put cos hyperbolic beta epsilon 0 is 2 by root 3. Then it will be minus kbt of ln 4 by root 3. But it's not given in terms of kbt, it's given in terms of epsilon 0. So that means you have to work a little bit hard by putting epsilon 0, beta epsilon 0 in terms of kbt. So here it will be, so tan hyperbolic beta epsilon 0 is half. So you will get e to the power beta epsilon 0 minus e to the power minus beta epsilon 0 by e to the power beta epsilon 0 plus e to the power minus beta epsilon 0 equals to half. Multiply throughout by e to the power beta epsilon 0 in the numerator and denominator. So it will be e to the power 2 beta epsilon 0 minus 1 by e to the power 2 beta epsilon 0 plus 1 equals to half. So that you will get, if you solve this, you will get 2 beta epsilon 0 equals to ln 3. ln 3. So that kbt, beta is 1 by kbt. So kbt is equal to 2 epsilon 0 by ln 3. So you'll get beta or kbt in terms of epsilon 0. So 2 epsilon 0 by ln 3. Substitute this here. So it will be, so your F, the free energy, I have to write it here. F1 is minus kbt ln, so it is minus kbt ln 2 cos hyperbolic beta epsilon 0. So this you will get, already cos hyperbolic is 2 by root 3. So it is minus kbt ln 4 by root 3 and kbt is 2 epsilon 0 by ln 3. So this is by root. Okay. So answer is 1A. Okay. So did you understand this problem?
Yes, sir.
All of you. Others, please respond.
Yes, sir.
Yes, sir.
Okay. Next question. Fermi energy. More or less every year, this question of Fermi energy comes either in 3D, 2D, or 1D. What is Fermi energy? This is the maximum energy of a fermion at zero, absolute zero temperature. So if you have this Fermi energy, now when we did this in 3D, let's say, how did we do? We have N. the number of particles is integral. So we did 4 pi v by h cube integral 0 to infinity in normal temperatures. Normal temperatures we have always Fp, Gp, Dp, p square dp. I should not write 4 because Gp contains 4 pi p square dp. And this Fp is the Fermi-Dirac distribution function. E to the power beta, so Z inverse e to the power beta EP plus 1, the Fermi-Dirac distribution function. So at zero temperature, T equals to 0, this Fp is 1. And the upper limit of the momentum is not infinity, but to that cutoff, which is known as Fermi momentum, Tf. So this is V by h cube integral 0 to Pf Gp dp. Right? Did you get it? So in 3 dimension, we have V by h cube integral 0 to Pf into 4 pi p square dp, and you integrate it, you will get something like this is V by h cube into p cube by 3 from 0 to Pf. So this Pf cube by 3. And there you will have a relation between Pf and N. So this is Pf cube by 3. So hence, Pf is directly proportional to the number density, that is N by V whole to the power 1/3. N by V whole to the power 1/3. So do you have I mean, you know how to calculate Fermi momentum. So Pf is directly proportional to small n to the power 1/3. If, on the other hand, this was a d dimension, Gdp dp is of the order of p to the power d minus 1 pp. Then n will be the hypervolume Vd by h to the power 3d, basically, or whatever it is. I'm not worried. It is directly proportional to integral 0 to Pf p to the power d minus 1 dp. So this is directly proportional to Pf to the power d. Pf to the power d. So Pf to the power d. Therefore, Pf is directly proportional to n to the power 1 by d in d dimensions. See, they will ask you Fermi energy, Fermi momentum, dependence. Every time 2-3 questions come. What is the Fermi momentum dependence on the number density, Fermi energy dependence on the number density. So PF is directly proportional to n to the power 1 by d. You should remember this. If you remember, then you don't have to worry about time. PF to the power d. If E is directly proportional to P to the power S, P to the power S, then EF is also directly proportional to PF to the power S. Therefore, EF is directly proportional to N to the power S by D. Now, if you want to calculate all the thermodynamic variables, again you will find P, the degeneracy pressure, that is the pressure at absolute zero due to fermions. Fermions provide pressure at absolute zero due to Pauli's exclusion principle, is again S by T, U by V. So if you have two dimension with non-relativistic case, EF is directly proportional to N. PF is directly proportional to N to the power half. If it is in two dimensions, then extremely relativistic case, that is massless fermions, then EF is directly proportional to N to the power half. PF is also directly proportional to N to the power half, obviously, because EF is PFC. Okay. Please note this. This is very important. This will come in every. So like CV directly proportional to T to the power D by S. EF directly proportional to N to the power S by T. P is equal to S by D into U by V is a general term. It can apply for any dimension D and any dispersion relation. E is directly proportional to P to the power S. So I think what is the time? I'll complete one last question. It's 10:58. Okay. So this came in GATE. Some year, I think. The previous 2019. A large number N of ideal bosons. Ideal bosons means whenever they say ideal bosons or ideal fermions means they are not interacting with each other. They do not have any inter particle potential. Okay. Each of mass M are trapped in a 3D potential. VR 3D potential VR equals to half m omega square r square. The bosonic system is kept at temperature T, which is much lower than than the Bose-Einstein condensation temperature, Tc. Then the chemical potential mu satisfies. There's a 4 options. So that means Bose-Einstein condensation is happening in this system. So there are 4 options given. So mu is less than equal to 3/2 h cross omega. Then 3/2 h cross omega. Some other things are also given is less than mu is less than equal to half h cross omega. Like this. Mu is greater than half h cross omega. So how will you do this problem? Can you tell me now? Any one of you? So can you tell me what is this kind of potential? Half m omega square r square. It's a quantum system. So what is the potential? What is this potential?
Harmonic oscillator.
Harmonic oscillator potential. It's a harmonic oscillator potential. So in this harmonic oscillator potential, what is the energy eigenvalues?
N plus half step.
Hmm? N
N
plus half
plus
h
half
cross
step
half.
omega.
This is a 3-dimensional harmonic oscillator potential. So what are the energy eigenvalues of a single boson? Here, a trapped boson. So it is a 3D harmonic oscillator. What are the energy quantum eigenvalues, energy eigenvalues of this 3D harmonic oscillator potential?
nx plus ny plus nz plus 3/2.
Okay, so it is n plus 3/2
Yeah.
h cross. N is some number, quantum number. Now tell me, what will be the chemical potential? What happens in Bose-Einstein condensation? Others, Ashwin, you tell me. What happens actually? What happens in this Bose-Einstein condensation? Hmm?
Sir, I don't know, sir.
No, what is the have you studied? All of you studied Bose-Einstein condensation? Because some 1 or 2 problems will be given from Bose-Einstein condensation. Others? Can you say? What happens in the Bose-Einstein condensation scenario. What happens to the chemical potential during Bose-Einstein condensation?
It becomes zero, I think so, sir.
Huh?
Does it
It
become
becomes
zero, sir?
it
Zero.
becomes zero. It becomes zero. So see, this Bose-Einstein distribution function FBE is what? 1 by e to the power beta into e minus mu minus 1. When e is equal to mu, this function blows up, tends to infinity when e equals to mu. Now, that means if whenever e equals to mu, then you will have Bose-Einstein condensation. But here, this, if it was, you say, okay, so mu is 0. Mu is 0 means then E should be 0. And when E is 0, then E is equal to mu. Then E minus mu is 0. And hence you have this distribution function blows up. And hence you have this Bose-Einstein condensation. But in this quantum Bose-Einstein Bose case, this is in a harmonic oscillator potential. This is in a harmonic oscillator. It's not free. Remember. So the ground state of a boson is 3 by 2 H cross omega. This is the lowest energy state of every boson in this harmonic oscillator potential. So mu must be less than equal to 3 by 2 H cross omega, need not be 0. But as soon as it goes to 3 by 2 H cross omega, Bose-Einstein condensation will start. So this is how the real Bose-Einstein condensate you can see in a trapped boson like liquid helium or gas 4 helium. Liquid, you will see Bose-Einstein condensation. So this Bose-Einstein condensation now will happen at a non-zero mu, which is equal to the ground state energy of this system. So this one mu is less than equal to 3 by 2 H cross omega is the correct answer. Okay, did you get it, all of you? Here the lowest energy state is not 0, but we have a 0-point energy, which is 3 by 2 H cross omega. So if mu is just less than or equal to, as soon as mu touches 3 by 2 H cross omega, Bose-Einstein condensation will start at any temperature T. Okay, so are you clear? Did you understand, all of you, this problem?
Sir, one doubt, sir.
Sir,
Yeah. Yes.
Sir, suppose if we didn't consider the harmonic oscillator potential means mu is equal to 0 will be the case. Is that what you're trying to say?
No. See, if you're free Bose gas, then EP equals to just P square by 2M. Free means only kinetic energy. There is no potential energy. Now, P square by 2M, what is the minimum energy? P will be 0. So minimum energy state will be 0. Exactly 0. But here, since you are considering a harmonic oscillator potential p square by 2m plus, now your energy is not a function of p alone. Your energy is a function of p and x, say one dimension. I'm just saying one dimension. X square. Its quantum version is n plus half h cross omega. A harmonic oscillator cannot have zero energy. The minimum energy of a harmonic oscillator is the 0 point energy, which is half h cross omega. Below this, there is no energy state of a harmonic oscillator, a quantum harmonic oscillator. It doesn't have any energy state below half h cross omega. This is its minimum energy state. So the minimum energy state starts from half h cross omega. So if the chemical potential touches this minimum energy state, then Bose-Einstein condensation will start. In this state.
Okay, sir.
All of the bosons, will be accumulated in this half h cross omega energy state. The all will be in the 0 point, having 0 point energy, rather. In this case, it is 3 by 2 h cross omega because it is in 3D. Okay, but in any ways, you cannot have 1D because in 1D, I told you again, Bose-Einstein condensation will only occur when D by S is greater than 1. So that's why they have put 3D. So D must be greater than S. So if they ask you whether non-relativistic Bose-Einstein gas will condense, whatever it be, if it is interacting or non-interacting, they will only condense when D is greater than S. So non-relativistic bosons will not Bose condense at 2 or 1 dimension.
Sir, one more thing I want to ask, sir.
Yeah.
Sir, somewhere I learned that in one dimension we cannot swap particles as if in statistics is. Is that the reason we cannot compute in one dimension?
Swapping?
Sir?
No, swapping because they see swapping particles
for
doesn't
statistics
mean
purposes.
Statistics.
So without interaction. So if we in one dimension, if we want to swap particles, means it is impossible. So without interaction, we cannot swap. And some long book I have learned something, sir. So is this the reason we cannot answer this question in one dimension?
See, the one dimension, you cannot swap particles. That is very correct. This because, let's say your particles are all in one line. If you want to swap particles, the particles must move in another dimension, right? To swap, the particles must move.
Yes, sir.
Let's say all of you are in one line and you are in a tunnel where all the walls are closed and you get sandwiched and everybody is in a line. How will one overtake another? To overtake, you need another dimension, right?
Yes, sir.